Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to do a quick crash course into organic chemistry functional groups. So this is really the who's who of what makes organic molecules, and it will really be useful as we go forward in talking about chemical reactivity to know what sort of different groups can give that reactivity. So most of the time, if we're looking at a general organic molecule, we're going to be trying to find different motifs. So things that aren't alkanes, and these are going to be called functional groups. So the ones we're going to be focusing in on today are heteroatom functional groups. So essentially where we throw something that isn't carbon or hydrogen onto an organic molecule. And here's pretty much the rundown of the major ones we're going to be looking at today. And just as a quick notation for how we represent functional groups. So what we're really looking at is various atoms, whether they're halogens, alcohols, or whatnot, attached to an organic molecule. And so the functional group is going to be what we're really showing here. However, you may notice there's something called an R group here. The R group is essentially a notation for some random organic thing. It could be a methyl group. It could be a 100-long carbon chain. It doesn't really matter because we're only interested in a very small section of the organic molecule. So when you see an R group here, just kind of ignore it. It's essentially a placeholder for a generic organic thing. However, what we're really interested at is what happens when we add a functional group to a molecule. This can adjust all kinds of properties that we're going to be pretty much spending the rest of the year diving into. So one of the simplest things we can add to an organic molecule is a halogen. So once we add it, we give it its salt name of a halide. So we're going to essentially treat these like they're an alkyl substituent, with the one major difference of instead of changing a suffix or anything, we're just going to add in a prefix. So if I add in a fluoroatom, we're going to add in a fluoro prefix, a chlorine atom, a chloro prefix, bromine, bromo, iodine, iodo, and that's pretty much it. So if I've got multiple of these halogens present in a molecule, we're going to list them in alphabetical order. So bromine first, then chlorine, then fluorine, and iodine last. And it turns out that these represent quite a number of common molecules you may have heard of. So this guy, for example, this is a methane molecule that we've added 3 chlorines to. So this would be trichloromethane, more commonly known as chloroform. Yes, the stuff that can knock somebody out. Quite potent, used in a lot of chemistry labs. So make sure that you always work at a very well ventilated place when you're working with chloroform. This guy, however, is kind of fun. Again, we've got a methane, but now we've got 2 chlorines and 2 fluorines. So this would be dichloromethane. This is actually one of the most common forms of freon, the common refrigerant. Turns out that if you add freon into the atmosphere, it can, well, consume the ozone layer and is actually quite toxic. And the reason why freon has been now banned. However, really what we have here is a methane molecule with a lot of very nasty things attached to it. And then we can also look at adding multiple groups on. So for example, this guy, we've got an ethane, but now we've got a dichloro, 1 on the first carbon, 1 on the second, and 4 fluorines. So this is tetrafluoro, 2 on the first and 2 on the second. So this is 1,2 dichloro, 1,1, 2,2 tetrafluoroethane. This is a member of the CFC family, along with freon, and these cause a major depletion in the ozone layer. So one of the big things of why we tend to see a lot of halides in a lot of common industrial products is because it turns out that the body is very bad at metabolizing halogens when they're attached to an organic molecule. And it turns out so are bacteria. This means that they last a long time in the environment, which causes some environmental issues. However, it also makes them very good for drug molecules. If I put a drug in your body, you don't want it to be immediately broken down. You put a halogen on there, it lasts longer. So this is both a good thing and a bad thing, because if it lasts long enough in the environment, it can really gum up the works and react with things that we need, like ozone. However, one of the chemist's favorite functional groups is alcohols. I wonder why. And you probably know alcohols most commonly as ethanol. So ethanol is the grain alcohol. This is the alcohol that causes alcohol to be alcoholic. And it is only mildly toxic in the body. And we call it ethanol because it is 2 carbons long, and we've now added an OH group. And anytime we add this alcohol OH group, we add an OL suffix, and it lets you know that we're working with an alcohol. And again, trying to place this on the main chain. So you can also have other types of alcohols like 2-butanol, or rack it up and you get something like 2,3-dimethyl pentanol, as well as plenty of other alcohols such as methanol or propanol, all of which have various levels of toxicity and can be fairly useful in a lot of environments. And one of the reasons why is when we add an OH group into an organic molecule, we've added a polar group to a non-polar molecule. And this makes the whole thing a lot more polar. And this will have some big advantages with how easy it is to mix organic molecules into water. So a lot of molecules that dissolve readily in water will have a lot of alcohols. A prime example of this is sugars. So for example, glucose has 5, count them, 5 separate alcohol groups. This makes it very easy to dissolve in water, whereas something like hexane would do a very bad job. However, we often give special names if I'm putting multiple alcohols on a molecule. So for example, if I've got 2 alcohols, we give this the name diol. And in this case, both of our alcohol positions must be specified. So for example, this first one is ethane diol. So specifically 1,2-ethane diol. This is more commonly known as ethylene glycol. This is commonly used in a lot of over-the-counter products because it's a very easy way to add an organic molecule, and it has a lot of good properties in keeping a mixture like, say, a shampoo well mixed into an aqueous solution. We also have things like 1,4-butane diol, where we have an alcohol on a butane at the 1 and 4 positions. However, there's plenty of other important alcohols. One cool thing you can do is you can put an alcohol on an aromatic ring, and this turns into something called a phenol, which should be distinguished from phenyl, which is a benzene substituent. So phenol actually has a lot of really cool uses. Most notably, if you have one of those throat sprays that cools your throat, that's essentially phenol acting as an analgesic. It short circuits your nerves, which is a good thing in low doses, but can be toxic in higher concentrations. But it's also, these phenol groups are also present in a lot of bigger organic molecules like tyrosine, another one of our 20 amino acids, which again has a phenol substituent on the end of an amino acid group. However, one of the cool things you can do with alcohols is you can take 2 alcohols and fuse them together, where you can now have essentially a carbon chain, an oxygen, and then another carbon chain. These carbon chains can be the same or they can be different. So in order to name these, we're going to simply name them by their 2 alkyl substituents. So ethyl and ethyl. So this would be a diethyl. Or ethyl and methyl. So this would be ethyl methyl. However, the official name treats the smaller group as an alkoxy group, which means that you'll simply put an oxy on the end. So let's take this first group. We could either be diethyl ether or ethoxy to represent this full group, and then ethane. This guy would be methoxy ethane or ethyl methyl ether. This guy, so again, we've got a phenyl and we've got a methyl. So methyl goes first alphabetically. So methylphenyl ether or methoxybenzene. All of these are okay names. And I want you to be familiar with all of them because any of them may show up on the ingredients list of, well, pretty much any sort of commercial chemical product you may see. And it's important to know what you're using. However, one of the big reasons I like to emphasize ethers is these are very nice ways to tie together two smaller molecules, and they do show up in a lot of commercial products. However, one of the things we can do is take a lot of these functional groups we just saw and modify their behavior by adding an important extra group called a carbonyl group. So this is a carbon double bond to an oxygen. You put it next to something, some random R group, and it modifies the behavior. And so one of the easiest things we can do is put this carbonyl group in between two carbon chains, and we get something called a ketone. So big thing where you can note that something is a ketone is it has a suffix of -one. And that's it. So here's three fairly common ketones. This first one, we have a propane. So this would be 2-propanone or propane 2-one, recognizing that we've got propane and we put a ketone on the center atom. This is more commonly known as acetone. Yes, this is nail polish remover. It is wonderful at removing a large number of very sticky organic substances. However, there's plenty of other groups like 4-chloro-3-methyl-pentanone. And here's one of my favorites. So here we've got a cyclohexane, so a hexane in a cyclic group, and it's got a ketone. Any carbon is as good as the next, so this is simply cyclohexanone. And you'll find ketones in a lot of very common commercial products. So just keep an eye out for those ones, and you'll be surprised at where they show up. So next special group here is if I put that carbonyl group on a primary carbon. Now it only has one organic neighbor and the other one is a hydrogen. These are called aldehydes, and they're often represented in condensed notation as CHO. So aldehydes are very reactive, so they have some really cool chemical properties, but often they're known to be very pungent flavors, very pungent scents. And you can recognize them by name because they have the suffix of al, as in aldehyde. So one of the ones we can start with is ethanol, 2 carbons, and it always has that aldehyde on the end. So we don't really need to reference the location of the aldehyde because we always know it's on the end. So this has the common name of acetaldehyde and is very notable as it's a toxic metabolic byproduct. So if you drink ethanol, your body turns that ethanol into ethanol, into this acetaldehyde. Ethanol is relatively okay for the body. Acetaldehyde is what causes hangovers. It is quite toxic, especially if you consume large amounts of ethanol. This builds up in your body, and this is what causes problems. Similarly, you can have this 3-methylbutanol. So we put that aldehyde on the 1 carbon, 1, 2, 3, place a methyl group there, and we have 3-methylbutanol. So this is what gives that multi-flavor in beer and cheese and coffee. So again, it's a very strong flavor. So if you have that kind of almost bitter taste, this is really what you're looking at. We also have benzaldehyde. So here's where I've got essentially a benzoic, a benzene group that I've put an aldehyde on. And this is what gives the classic almond flavoring. So if something like tastes or smells of almonds, this is usually what you're recognizing. So the next thing we can do is put that carbonyl group next to an ether. So if you do that, you turn that ether into an ester. So esters are very commonly known for very strong smells. So if you smell something in the air or in a fragrance, there is a very good chance you're looking at an ester. So one of the big things is that esters tend to have two-part names. So they'll have the alkyl component, so whatever is over here, that's going to simply be named as an alkyl group. However, the main chain here will have a suffix of ate. So for example, on this first group, we have ethyl, 1, 2, 3, 4, butane. So this becomes ethyl butyrate. So this is the classic smell of pineapple. So if you have something that has artificial pineapple flavoring, it usually will have ethyl butyrate. In this case, we've got 1, 2, 3, 4. So now we've got butyl acetate. So this is apple. And I like emphasizing how important it is that you have the ethyl group and the butyl group on the right end. Because here we have the 2-carbon substituent on this side, and we have pineapple. In this case, the 2-carbon substituent is on the carbonyl side, and we have apple. Quite different effects, even though the chemical structure is only slightly different. However, there's one ester I will want to point out. It doesn't follow classic naming convention simply because it's old enough and important enough, and that's methyl salicylate. So this group here is called salicylate, and here we have the methyl group. This is most commonly known as the center flavoring of wintergreen, and we will make this in lab. It is quite cool and quite impressive. So the next important functional group is carboxylic acids. So this happens when we put a carbonyl group next to an alcohol, and this generates a classic COOH behavior. So if you see this in a condensed notation, we have a carboxylic acid. And almost all of the acid behavior in organic molecules is due to the presence of carboxylic acid. So this is one of the most important functional groups to recognize. So this can almost always be recognized by having the oic acid suffix. So these are some of our classic oxy acids. So here we've got an ethanoic acid, 2-carbon chain and an acid group. This is also commonly known as acetic acid. This is the active component of vinegar. Here we've got salicylic acid. So I've turned my ester into an acid, and suddenly I go from wintergreen to a very effective acne treatment. Now, if you go ahead and turn this alcohol into into its own ester, you suddenly generate acetyl salicylic acid, and this is aspirin. So wintergreen, acne treatment, and aspirin, all very closely related. Now, a very important feature is you can pull a proton, so a single hydrogen atom without its electron, so a plus positively charged proton or hydrogen atom, off of a carboxylic acid, and you can generate a carboxylate. So this is a common base present in a lot of organic molecules. So this frequently occurs in a lot of organic species as some sort of intermediate, and you can also place this in a lot of solutions to act as a preservative. So big thing is carboxylates follow the carboxylic acid nomenclature, except for now we've replaced that ic with an ate. So ethanoic acid now becomes ethanoate, more commonly known as acetate, which is again a very common preservative. You probably see this as sodium acetate. And here we've got benzoic acid loses a proton and it becomes benzoate, which again is a very common food preservative, often as sodium or calcium benzoate. Now, our last important functional groups here are going to be anything that contains nitrogen. So if we have a classic alkane and we put in a nitrogen atom, we've now generated an amine. And this amine can either be primary, and one of the reasons we really care about these amines is that they're very important in acid-base reactions, as we'll see later, and they're very useful in binding metal ions. So if you want to try and bind up and reduce the presence of metal ions in solutions, you'll often end up generating amines. And this is one of the reasons they can often be used in cleaning solutions, such as Windex, which has its own form of amine. Now, one of the big things that we want to make note of is that these amines can be bound to 1, 2, or 3 carbon chains, very infrequently 4, but these are the common 3 you'll see. So when we're naming these, we can have essentially primary, secondary, or tertiary amines. We're going to name the longest carbon chain with an amine suffix. All the other substituents are referenced as N-alkyl, meaning that I've got this alkyl group at the N position. So for example, for a primary group, we have a propyl group. So this would be propane to amine, representing I've got an amine on the second carbon of propane. Here, I've got a single methyl group, that's my small substituent, and the long one is 1, 2, 3, so propane. So this is N-methyl propane 1-amine. And here we still have that propyl group, but now we've got 2 methyl groups. So it becomes NN dimethyl propan 1-amine. And again, I'm not necessarily expecting you to be able to name these, but recognize what sort of functional groups may be occurring based on name alone. Now, our last important functional group, and this might be one of the most important, is an amide. So in this case, we place a carbonyl group next to our amine, and this generates the amide group. So again, this nitrogen can be attached to 1, 2, or 3 additional carbon atoms, typically 1 or 2. And the chain containing the carbonyl group is going to be our amide, no matter its length. And then everything else will be referenced based on the N-alkyl nomenclature. So one example is propanamide. And again, don't need to designate what carbon the atom, the amine occurs on, because it's always going to be terminal. However, we also have some very cool species, like hydroxylphenyl ethanamide. So we have an ethanamide with a phenyl group, a hydroxyphenyl group attached. And this is Tylenol. So again, a very cool organic molecule, but it also contains a very special, an example of a very special type of bond. And this is the bond in between a carbon atom and a nitrogen atom. This is often called a peptide bond. So one of the reasons this is important is that amides are very good at holding together 2 different groups. So 1 long chain here and 1 long chain here. And you can make and break these peptide bonds fairly easily. And it turns out that these peptide bonds are what hold together multiple amino acids in order to form larger proteins. So when we are looking at a protein, what we've really done is we've taken an amine and a carboxylic acid, tied them together, and holding all life together with a single peptide bond. So that's our crash course in organic chemistry. Next time, we're going to be diving a little bit more into the natures of bonding and molecules. Until then, take care.